So, hello everyone. How are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about this thing. This is Riemann Zeta of 1. And for descriptive detail of this one, I have written over here the Riemann Zeta of 1. Now, you would say, what is like if you have never listened about Riemann Zeta function? So I'll just get back to you over there, don't worry. This video is gonna be from scratch, right? Yeah. And I'm just gonna consider that you have never seen the Riemann Zeta function and from where this is coming from and everything. And look, whatever we are gonna use here, I have proven in my previous videos, and I'll paste the link of those videos which I'm just gonna use here to prove this down. Actually, you know what? If you are a daily viewer of my channel, so you must have recognized, or maybe you must have seen one of my videos with thumbnail with like this is 3, right? So Riemann Zeta of 3, although it was not correct because Riemann Zeta of 3 cannot be represented as in a closed form that that looks like some pi terms, like including pi, right? But now we ain't gonna do the same thing as we did for here with this one. We are just gonna represent the Riemann Zeta of 1 like incredibly. It's gonna be an incredible equation, I would say, literally. And I'm damn sure you must have never seen this before. I'm damn sure about that. And this is, again, I would like to give the whole video's credit to me. It's me. I have just proved this by myself. Until now, I have studied a lot of mathematics, and I have a great interest in. I have had a great interest in like Riemann Zeta function, and you know about that. So, and I have never seen this before, right? So that's why. And you know what? Some crazy things is, you know what? Let me just show you something. You would say, well, we'll come to Riemann Zeta function, but before that, what we are going to use in this video, mostly, we have, well, it's this, like the thing that I'm going to writing here. I have proved this, and that's the that's the most latest video of mine in which I have proven this. So this is pi z cotangent of pi z equals 1 minus 2 times the sum as n goes from 1 to infinity of Riemann Zeta of 2n and z to the 2n. So I have proven this, right? Although we have proven this, I have proven this using this thing, pi cotangent of pi z equals 1 over z plus. So I would request you to just watch the proof video of this one, right? Because we are gonna begin our proof of Riemann Zeta of 1 from here itself. And another thing is there, I'll just get you over there. But before, we can just prove this one from here, right? And it's 1 over z plus n and plus 1 over z minus n. And actually now you would say, what about this? So even I have uploaded the proof of this equation as well, right? So you can just consider watching the proofs of these two equations. You can find it on my YouTube channel, and I'll just paste the link of these two videos in my description box. Don't worry. And the second thing is that, the second thing is Weierstrass infinite. Oh, wait a second, I think I should consider that board. And again, Weierstrass infinite product of gamma function, right? So it is Weierstrass infinite product of of gamma function. And wait a second, yeah. Actually, again, I have proven this one as well, right? And I'll paste the link of this one as well in the description box. So it's 1 over gamma z equals z times e to the Euler-Mascheroni times z, right? And then the product as n goes from 1 to infinity of 1 plus z over n and e to the z, wait a second, e to the negative z over n. So this is your Weierstrass infinite product of gamma function, right? Well, it's the reciprocal. It's representing the reciprocal of the gamma function, I'm sorry. Okay. And the last thing, like these things are the most influential and most dominating things that we are going to begin our proof with. But we are going to use some basic things between the proof actually. And one of those things are, it's not basic at all, it's crazy. Euler's reflection formula, last but not the least actually. So basically you know about that. It's gamma of 1, wait a second, gamma of z times gamma of 1 minus z equals pi over sine pi z, right? And you, if you are not familiar with this one, so I would like you to just take a look at this one. Although we have talked about this in my introductory video of gamma function, right? So basically it's z times gamma of z equals gamma of 1 plus z. Yeah. So these things are the, I would say you should just note all these things down if you have a notebook right now, and then you should just begin the proof. Or if you haven't watched the proof videos of these three things, and maybe I have proved, yeah, I'm sure about this. I have proven this one. This one I prove in the video. I will prove this one in the beginning. In the between of the video when I'll just use that one, so it's not difficult to prove, right? Okay, so I would request you to just watch the all 4 videos, this one, this one, this one, and this one, the proofs of all those 4 things, and then you should just come up here and watch the rest of the proof of Riemann Zeta 1, right? Okay, now we are here with our tools and we are good to go with our proof. Wow, this is gonna be crazy. And again, I'm gonna take time. I'm not gonna just finish it up. Wow, that's like a cake, a piece of cake. No, it's gonna take a time, and yeah, we have time. What's wrong? Let's learn mathematics. Okay, so basically we are having this equation. This looks good, right? And now let's just do something here. So I'm just gonna write here integrating both sides with respect to z. We can do that, right? Okay, so integral, oh wait a second, but before that let me just do something here. Okay, before that let's just isolate this infinite sum, right? And how are we gonna do that? So let's just add both sides with 2 times this sum. So that's gonna give us pi z cotangent of pi z plus 2 times this sum as n goes from 1 to infinity of Riemann Zeta of 2n is z to the 2n equals 1. And now subtracting both sides with pi z cotangent of pi z. So it's 2 times the sum as n goes from 1 to infinity of Riemann Zeta of 2n is z to the 2n equals 1 minus pi z cotangent of pi z. And the final thing here is dividing both sides with 2. So basically we have successfully isolated, wait a second. Yeah. So we are having Riemann Zeta of 2n and z to the 2n equals 1 over 2 minus pi over 2 z cotangent of pi z. Okay, so I think you guys are good to go with this. And you know what? Like, it's one of my latest videos in which I have integrated this equation actually, and we just had reached up to this equation. I think this thing. It's the Riemann Zeta of 2n, and it was over n times 2 to the n came out to be negative l into. So basically in this video I have integrated this equation, but it's alright. I'm not gonna just recommend you to watch this video to just watch the integral of this part. Let's just do this because I have promised you we will be doing this from scratch. But those things were prerequisite, right? And you have to just consider those things firstly. So now we're just gonna integrate this equation with respect to z, dz, and I'm having dz here. So basically, on the left hand side, we can say due to linearity, this sum and this Riemann Zeta of 2n is gonna. Oh my goodness! Like, why I'm just hurrying up here? Oh, wait a second. We are left with a last thing here that we must have done before, but it's all right. Basically, dividing both sides with z actually, and the last step. So this is gonna be 2n over like minus 1. So that's gonna be 2n minus 1, right? Riemann Zeta of 2n, z to the 2n minus 1. And here we are having 1 over 2 times z. And this z cancels out and we are having pi over t. Pi over 2 cotangent of pi z. Okay, now we are successfully here to integrate this with respect to z. Okay, so again I just explained you that due to linearity we can say, so it's the sum as n goes from 1 to infinity of Riemann Zeta of 2n and integral of z to the 2n minus 1, right, dz equals, and when we talk about the integral of this part, so it's going to be 1 over 2 integral of 1 over z dz, and then minus pi over 2 integral of cotangent of pi z dz, right? I hope you guys are like visible there and you guys can see all the stuffs. Okay, so well, don't worry, I'll just write the steps. I'll write the step down over here again. Okay, so yeah, so basically we have integrated, right? And here we are having the sum as n goes from 1 to infinity of Riemann Zeta of 2n integral z to the 2n minus 1 dz equals 1 over 2 integral of 1 over z dz, right? And minus pi over 2 integral of cotangent of pi z dz. Now let's just talk about the integral of pi z. I'm sorry, the integral of cotangent of pi z. So integral of cotangent of pi z dz. Wait a second. Yeah. We can write this as cosine of pi z over sine pi z, right? Okay. And we know that the derivative of sine is cosine, but we have to just change the variable. Let pi z equals t. So dz is gonna be dt over pi. It means we would be having 1 over pi and integral that's gonna be cosine of t over sine of t. We are having the derivative of the denominator in the numerator, so that's gonna be ln of the denominator. So 1 over pi ln of sine t, and t is pi z. So hence we are having this stuff after integrating that cotangent of pi z, right? And we know the integral of z to the 2n minus 1, although I have proved the most basic formula of integration, that's the power rule, so you can consider watching that as well actually. And the integral of 1 over z is ln z, we know that. And again, if you want the proof of that as well, so you can just consider just asking me in the comment section. I'll just get back to you as well over there. So it's the sum as n is going from 1 to infinity of Riemann Zeta of 2n, and this is gonna be z to the 2n over 2n, right? Okay, that's gonna be 1 over 2 ln z, and that's gonna be minus pi over 2. Wait a second, is minus, and it's, oh wait, 1 over pi ln of sine pi z. So this pi we got rid of that, and we can just take a look here. This 1 over 2 cancels out with these two things, and finally we are having with our last expression of this thing, that is Riemann Zeta of 2n z to the 2n over n, right? Wait a second, equals, it's ln z minus ln of sine pi z. Okay, so now you would say, now what? We just got reached up to here, and now what? Now what should we do here? Oh, now we're gonna just take a look at some magics in mathematics. Wow. And we are very close to use the reflection formula, but not the gamma function. I'm sorry, the Weierstrass product. Why I'm using marker. Okay, so we know that ln of a minus ln of b equals ln of a over b, right? So for our case, a is z and b is sine pi z, right? So let's just consider watching this thing in this reciprocal manner or something like that. So basically our sum is gonna be Riemann Zeta of 2n z to the 2n over n equals, this is ln of z over sine pi z. Now, wow, this is amazing. Using Euler's reflection formula here now. And how are we gonna do that? Wait a second, it's interesting. So we know that gamma of z times gamma of 1 minus z equals pi over sine pi z. And now dividing both sides with pi and simultaneously multiplying both sides with z. So that's gonna be z times gamma of z times gamma of 1 minus z over pi, right? And that's gonna be z over sine pi z. Let's take a look at the argument of natural logarithm on the right hand side of this equation and take a look at here, right? So this is how it's gonna relate. And you know what, I hope you remember that we have talked about in the beginning of this video. So z times gamma of z is gamma of 1 plus z. Let's just prove this down. You know what, gamma of 1 plus z is z factorial, right? So if we consider, and then gamma of z is gonna be z minus 1 factorial, and z times z minus 1 factorial is gonna be z factorial. So hence z times z minus 1 factorial, here we are having z factorial, and z times z minus 1 is z factorial, hence proved. So that was pretty easy actually. That wasn't difficult at all. So hence we can just replace this z times gamma z with gamma of 1 plus z times gamma of 1 minus z over pi equals z over sine pi z. And now we're gonna just replace this argument with gamma of 1 plus z times gamma of 1 minus z over pi in our equation. So this is how you can relate. Wow. Look, let me tell you something. When I was just doing this, right? When I was doing this, I was like, oh my god, the things that I'm having it's interesting. So our sum is gonna be Riemann Zeta of 2n z to the 2n over n equals ln of gamma of 1 plus z times gamma of 1 minus z over pi. And now, if you're having some notebooks, so I would like you to just note this down, because from now onwards we are gonna play with the Weierstrass product, and that's gonna be complicated. Well, I'll make sure it's not a be complicated, but it's all right. Mathematics is all about, it cannot be done by simple things. So Riemann Zeta of 2n z to the 2n over n equals ln of gamma of 1 plus z times gamma of 1 minus z over pi. Although we can just write this as ln of gamma of 1 plus z times gamma of 1 minus z and minus ln pi. So we can just write this as, or let's just consider this thing for now, and now we're gonna play around with the Weierstrass product. So we know Weierstrass product, right? But before that, let me just check something here. Okay, so we have reached 21.5 minutes, right? Okay, so we know that it's 1 over gamma of z equals z times e to the Euler Maclaurin times z, and times the product as n goes from 1 to infinity of 1 plus z over n e to the negative z over n. Right? Okay. And now you would say, Aman, what are you going to do with this? So, taking reciprocal of this, it's gonna help us out. We can do that. Although, on some part, whenever you learn about this, you will get to know the reciprocal of that, right? Because that's important, because it's quite rare that we deals with the reciprocal of the gamma function, right? But it's all right. So if you're gonna take the reciprocal of this one, so that's gonna be gamma of z, and this is gonna be e to the negative Euler Maclaurin times z over z, this one, and times the product as n goes from 1 to infinity. And wait a second. So this can be written as this argument can be written as n plus z over n. So if you're going to take the reciprocal of that, so that's going to be n over z plus n, right? And this is going to be e to the z over n. I hope you guys are fine with this, and I don't think that it's difficult to just understand that, right? And it's easy, I would say. Let me just drink some water, and then we will just over there. We will be working over there. Okay, so here we are having this much stuff, right? And now we want the product of 1 plus z times 1 minus z, obviously in the gamma function. So firstly we are going to take a look for 1 minus z. Gamma of 1 minus z. So basically you have to replace z with 1 minus z all over this equation. So it's gonna be e to the negative Euler Maclaurin times 1 minus z over 1 minus z times the product as n goes from 1 to infinity of 1 over it's 1 minus z plus n, right? And it's e to the 1 minus z over n. Okay, so we are having this thing, right? And now let's just replace z with 1 plus z. So it's gamma of 1 plus z, right? So e to the negative Euler Maclaurin 1 plus z over 1 plus z, and times the product as n goes from 1 to infinity of n over 1 plus z plus n, right? Yeah, that sounds good. Yeah, and e to the 1 plus z over n. And now we have to just multiply those two equations in order to get the argument of natural logarithm in our final equation actually, in our target equation actually. So, yeah, so gamma of 1 plus z times gamma of 1 minus z is gonna be e to the negative Euler-Mascheroni 1 plus z over 1 plus z times the product as n goes from 1 to infinity of n over 1 plus z plus n. Or maybe we should write this as we should write this as n plus 1 plus z, right? And e to the it's 1 plus z over n, and times e to the negative Euler-Mascheroni 1 minus z over 1 minus z, and times the product as n goes from 1 to infinity of n over n plus 1 minus z and e to the 1 minus z over n. We have to just talk about the product of this thing, right? So now let's just multiply all the stuffs with each other. So this e and e gonna multiply, right? So that's gonna be, well, I think yeah, let's just multiply. So it's gonna be e to the, because the e and e, the bases are same, so that's gonna be negative Euler-Mascheroni times z, multiplying this negative Euler-Mascheroni in this parenthesis, and then adding this one as well. So negative Euler-Mascheroni and plus Euler-Mascheroni times z, because negative times negative is going to be positive, right? I hope you guys are like relating this. I think it's not difficult. And 1 plus z times 1 minus z in the denominator, it's gonna be 1 plus z times 1 minus z. And if we talk about the product, so that's gonna be a single product actually, and the arguments are gonna multiply. So the single product as n goes from 1 to infinity, and it's n times n squared over n plus 1 plus z, and times n plus 1 minus z. So let's consider n plus 1 equals a and z equals b. So a plus b and a minus b, a square minus b square, right? So that's gonna be n plus 1 whole squared minus z squared. I hope you guys, and that's why I just wrote in like something like that instead of this one. Okay, and then again e, so that's gonna be e to the 1 over n and plus z over n and plus 1 over n minus z over n. I hope you guys are perfectly fine with this, and I'm just expecting that you guys are understanding each steps. So now plus z over n minus z over n, we just got rid of that thing, and here we are having negative Euler-Mascheroni times plus Euler-Mascheroni, so that's gonna be 0 as well. Actually they're gonna cancel out with each other, and now we are having something pretty, I would say, rather than these two products actually, right? Okay, so we are having, and here 1 plus z over times 1 minus z, it's gonna be 1 minus z squared, right? And e to the this negative Euler-Mascheroni times, negative Euler-Mascheroni and negative Euler-Mascheroni, negative 2 Euler-Mascheroni, yeah, and it's 1 minus z squared and times the product as n goes from 1 to infinity of n squared over n plus 1 whole squared minus z squared, and it's e to the 1 over n plus 1 over n 2 over n, and this is equals to gamma of 1 plus z times gamma of 1 minus z. This Isn't this amazing? And now I'm just taking natural logarithm both sides. Like, oh my goodness, this is really disgusting or maybe extraordinary stuff. Like, look at this. We have to take the natural logarithm of this big chunk of things, and that's gonna be complicated, I would say. Wait a second, let me just check if the recordings. Yeah, the recording is going on perfectly, and let's just take the natural logarithm. Take the natural logarithm both sides, right? Both sides actually. So in order to get this part, right, and then we will just plug the stuffs that we are going to have after taking the natural logarithm of left hand side, like this thing over there, in order to get something great here. Okay, basically Riemann Zeta of 1. Wait a second, that's gonna be amazing. I think I should consider erasing this board, right? Okay, and then let's take the natural logarithm. So you know that let me just take some break with that one, but let's come to the natural logarithm. So natural logarithm. So we know that ln of a minus ln of b is going to be ln of a over b, and ln of a plus ln of b is going to be ln a b. And if we are going to take the natural logarithm of a product, so that's going to be, let's say this is something, the argument, so that can be written as the sum and times ln of that argument. Actually, you know what, just imagine a product and you are taking the natural logarithm of that. So this product can be written as ln a plus ln b, right? It means that if we're taking a product, the natural logarithm of product, so we can just consider writing it like each term with natural logarithm in front, adding, like, I hope you're getting that. Like I'm saying ln of 5, ln of, wait a second, ln of 5 times 4 times 3 times 2 times 1 can be written as ln of 5 plus ln 4 plus ln 3 plus ln 2 plus ln 1 actually is 0, right? But let's write this down. So yeah, so here we can just say it's ln product 5 n equals 1 n, right? And this is sum ln as n goes from 1 to 5, and it's ln of n. Obviously, so that's how, that's why, like, I'm just explaining you this because we are going to use this here, right? Okay. Now we are good to go with our natural logarithm both sides. That's amazing, yeah. So we have ln of that thing. So e to the negative 2 times Euler Mascheroni over 1 minus z squared and times the product of n squared over n plus 1 whole squared minus z squared, and it's e to the 2 over n, and equal the ln of that gamma of 1 plus z and times gamma of 1 minus z, right? It's alright, I'm not gonna write that down. Okay, so now we can consider breaking these apart. How are we gonna do that? So basically this term, like this big term is the argument of the product. So we can use the product rule here, like this one. And if we talk about this one, so it's ln of a over b, so that can be written as ln of a minus ln of b, and times this one. So it is ln of e to the 2 times Euler Mascheroni and minus ln of 1 minus z squared and plus ln, because it's in the product of the product of n squared over n plus 1 whole squared minus z squared e to the 2 over n, right? And we know that, okay, natural logarithm of e to the something, it's gonna be the power of that. the exponents of that. So it's 2 Euler Mascheroni, 2 times Euler Mascheroni, minus ln of 1 minus z squared, and plus, this is gonna be in sum, infinite sum actually, as n goes from 1 to infinity of ln of this argument, n squared e to the 2 over n over n plus 1 whole squared minus c squared. And now you would say, let's just break this using some natural logarithms as well as we did for these two things. Wow. Let's just expand that as well. Isn't that amazing, guys? Like, we are like, wow, playing with mathematics. So, and here we can consider writing ln n squared plus ln e to the 2 over n and minus this denominator along with ln. So it's gonna be 2 Euler Mascheroni minus ln of, I'm sorry, it's negative 2. So it's negative 2 Euler Mascheroni. I'm sorry, I just messed up there. So it's negative in front. Okay. So it's 1 minus z squared and plus the sum as n goes from 1 to infinity of ln of n squared and plus ln of e to the 2 over n and minus ln of the denominator n plus 1 whole squared minus z squared and this parenthesis. Ln of a to the b is b ln a, right? We know that. And ln of e is 1, so that's how we wrote this down. Ln of e is 1, so that's how we wrote this down as negative 2 Euler Mascheroni times ln e, and ln e is 1, that's why. But for now, here we are having ln n squared, so it's going to be 2 times of ln of n. Okay. So here we are having negative 2 Euler Mascheroni, negative 1 minus z squared, plus the sum as n goes from 1 to infinity of 2 times ln of n, natural logarithm of n, and plus it's gonna be 2 over n, and ln of e is gonna be 1, and minus natural logarithm of n plus 1 whole squared minus z squared. That's cool. That's amazing. And basically, if we subtract both sides with ln of pi, so here we are having ln of gamma of 1 plus z times gamma of 1 minus z, this term, and minus ln pi, this term. This big chunk of thing is equal to this one actually. This sum. This one. That's amazing. Like, it's really amazing. Wow. So yeah, we are very close to our end. Not ours, but this thing's end actually. And just take a look. Like, you have to be curious and you have to be focused from now. Because now I'm just going to incarnate the Riemann Zeta of 1 from here. So we are having this sum as n goes from 1 to infinity of Riemann Zeta of 2n z to the 2n over n equals this thing. So it's negative 2 times Euler Mascheroni minus ln of 1 minus z squared, and I'm considering writing this negative ln pi over here, and then this sum. So it's 2 times natural logarithm of n, and then we are having plus 2 over n and minus ln of n plus 1 whole squared minus z squared. Okay, so yeah, we are having that much things. And now we can just consider writing this sum in terms of 3 separate sums, right? How we can write that down. So basically our sum, or let's just let's consider adding both sides with these terms, right? So that's gonna be 2 times Euler Mascheroni plus ln of 1 minus z squared plus ln pi and plus the sum as n goes from 1 to infinity of Riemann Zeta of 2n and z to the 2n over n, right? And on the right hand side we are having some 3 sums. The sum as n goes from 1 to infinity of the first one, so 2 plus, let's consider writing it as 2 times natural logarithm of n and plus the sum as n goes from 1 to infinity. Let's just plug 2 out of this sum and it's 1 over n. Here it is, the Riemann Zeta of 1. Here it is incarnated, oh my god. And the last sum, the sum as n goes from 1 to infinity of natural logarithm of n plus 1 whole squared minus c squared. Okay, so now we are gonna subtract both sides with this sum and add both sides with this sum simultaneously, and we would be left with this 2 times the Riemann Zeta of 1 on the right hand side. Let's just do that. Oh, I think I didn't clarify the Riemann Zeta function in the beginning of the video. Oh my god, you're gonna just blow my mind that Aman, you didn't explain it to us. So it's, let me just explain it to you. Riemann Zeta function actually. So basically, it's the Riemann Zeta of S equals the sum as n goes from 1 to infinity of 1 over n to the s. So basically that's the Riemann Zeta function. And you know what? Riemann Zeta of 2 is pi squared over 6, or Riemann Zeta of 4 is pi to the 4th over 19. I have proved this several times, and if you want, I can just paste the link of the playlist of this Riemann Zeta of 2. Although I haven't proved that, I have proved this, but personally, not officially on YouTube channel. So maybe I'm just gonna bring some videos over that as well. And the Riemann Zeta of 2 is also known as the Basel problem, and it was solved by our greatest mathematician, one of the greatest, I would say, Euler. Okay, Leonardo actually. So let's just subtract both sides with this sum. So it's 2 times Euler Mascheroni plus ln of 1 minus z squared and plus ln of pi plus the sum as n goes from 1 to infinity of Riemann Zeta of 2n z to the 2n over n and minus the sum as n goes from 1 to infinity of 2 times natural logarithm of n and adding both sides with this sum simultaneously. So it's gonna be this sum as n goes from 1 to infinity of natural logarithm of n plus 1 whole squared minus z squared. And as explained you the Riemann Zeta function. So if you replace s with 1, so that's gonna be this sum. So basically it is 2 times Riemann Zeta of 1. That's pretty cool. And now we are having 3 sums on the left hand side. So we will consider writing it as a single sum and just adding their arguments with each other. So it's 2 times Euler Mascheroni plus ln of 1 minus z squared plus ln of pi and plus the sum as n goes from 1 to infinity. So it's the Riemann Zeta of 2n z to the 2n over n and plus wait a second, minus this argument. So it's negative 2 natural logarithm of n and plus this argument natural logarithm of n plus 1 squared minus z squared, and this is equal to 2 times of Riemann Zeta of 1. Okay, now let's do our final thing here in order to get our it's the second final thing actually. since we're having n here, so we can just consider multiplying this n to this one as well as this one to just write n as a common denominator over there. So it's 2 times Euler Mascheroni of 1. Let me just write it in a manner. 1 equals 2 Euler Mascheroni plus ln of 1 minus z squared plus ln pi and plus this sum as n goes from 1 to infinity. So it's Riemann Zeta of 2n z to the 2n and minus 2n times natural logarithm of n and plus n times natural logarithm of n plus 1 whole squared minus z squared over n. And now let's just divide both sides with 2 in order to get the Riemann Zeta of 1. Oh, this is mathematics. This is mathematics. So Riemann Zeta of, wait a second, guys. Riemann Zeta of 1 came out to be 2 over 2, it's Euler Mascheroni, plus 1 over 2 ln of 1 minus z squared and plus 1 over 2 ln pi and plus 1 over 2 the sum as n goes from 1 to infinity of Riemann Zeta of 2n z to the 2n, negative 2n natural logarithm of n and plus n natural logarithm of n plus 1 whole squared minus z squared over n. Here is the closed form of the Riemann Zeta of 1. Guys, now I would request you to just dive into it, to just like, this is deep, this is really deep, this is mathematics. That's why I love to play around with these things. The way we used the Weierstrass product, the way we used the Euler's reflection formula, the way we used the both expressions for the cotangent function as an infinite sum, right? And we just ended up with the Riemann Zeta of 1. Like literally, it's basically, you know what Riemann Zeta of 1 is? It's limit n tends to, let's talk about this here. And yeah, so you know about harmonic numbers. So harmonic numbers actually, so basically it's the sum of reciprocals, natural reciprocals up to 1 over n. So this can be written as the sum as k goes from 1 to n of 1 over k. And when we take a limit n tends to infinity, so basically this is your Riemann Zeta of 1. This is your Riemann Zeta of 1. We are talking about the harmonic numbers up to infinity, and that too equals to the Euler Mascheroni plus 1 over 2 times the natural logarithm of 1 minus z squared plus 1 over 2 times the natural logarithm of pi plus 1 over 2 times the infinite sum as n goes from 1 to infinity of Riemann Zeta of 2n times z to the 2n minus 2n natural logarithm of n plus n natural logarithm of n plus 1 whole squared minus z squared over n. That's cool. That's amazing. I don't know what I have done here, but whatever I have did, it was mind blowing and so crazy. The way we just incarnated the Riemann Zeta of 1 here. So Again, guys, if you got to learn something from this video, obviously you did. I'm damn sure about that. So just make sure to like, subscribe, and share. And if you have any kind of doubt so far, you are free to ask me in the comment section. And again, just Riemann Zeta of 1. Okay, that's cool. That's the spirit of mathematics. Yeah, guys, I think we should just leave now. And it's been around 50 minutes. Yeah, it's past 50 minutes actually. So, goodbye, guys. Take care. Love you. And stay tuned for some next videos, because this is maybe something of me. This is mine. Goodbye, guys. Love you.